here. Let me introduce her by her short bio. Dr. Yan Liu is a professor in the Computer Science Department and the director of Machine Learning Center at the University of Southern California. She received her PhD degree from Carnegie Mellon University. Her research interest is machine learning and its applications to climate science, healthcare, and sustainability. She has received several awards, including the NSF Career Award, Okawa Foundation Research Award, New Voices of Academies of Science, Engineering, and Medicine, Best Paper Award in SIAM Data Mining Conference. She serves as general chair of several conferences like KDD 2020 and ICLR 2023, and program chairs of WSDM 2018, SDM 2020, KDD 2022, and ICLR 2022. She will present her research on frontiers of foundations model for time series modeling and analysis. Let's give her a big applause. Yeah, thank you. Thank you for Professor Lee for the introduction. And I really want to have a big thank for the organizers for inviting me. I'm really excited to talk about my research work for probably my whole career around time series. So we basically are experiencing, here we go. Okay, so we're now experiencing a huge explosion of AI technologies, and then ever since that we have our first started from the ImageNet, and then we see AlphaGo with the DeepMind, AlphaFold, and now basically we have ChatGPT. We always think that AI is going to play a major role in devising solutions in addressing many of the societal challenges we're facing. So as we move forward, we started to thinking about what will be the next step, right? What will be the future of AI research besides reinventing large language model? Then that's where I started to think a little bit about more of how we think about, our universe and our world. Einstein has this famous quote to say that a human being is part of a whole, whereas universe is actually a part limited in space and time. And that means that a lot of our interactions with the world is actually centered around the spatial and temporal directions. And then from that perspective, that I think for the next step, AI is going to address many of the challenges in our society where we're going to interact and obviously have to devising solutions to addressing representation learning and effective modeling for spatial temporal data or time series data in general. For example, there has been a big push for AI for climate science, where we're going to collecting or have simulation data around climate-related factors such as CO2 concentration, precipitation, wind, temperatures, and etc. We want to predict the heat wave. We want to predict, the drought and etc. And obviously how we can actually address some challenges for this climate change. And these time series data also will vary across different locations, and that is why it is actually spatial temporal data. Another example that we have seen is I'm not sure if this actually works. The projector, where is? Oh, here we go. That's why. Here. Yeah. There is some battery, I think. Yeah, but it's not moving. Yeah, I was joking with my neighbors that AI can address many of the challenges, but some small technical glitches still we have to rely on human to resolve this issue. It's working perfectly. Is my screen freezing? If not, I guess somebody can press, I can say next page and then we can move forward. Oh yeah, now it's working. Or maybe somebody pressing it for me. We're good. Okay. All right. Sorry for the technology glitch. Hopefully next year we'll solve this by AI technology. So yeah, another application we also work a lot is around AI for healthcare application. For example, we've been working on patient monitoring in the ICU room. I was at first hand actually able to enter the pediatric ICU room when the doctors introduced me to the project. And when I see a child was really suffering from even breathing as a normal person would think it's just by default, that I felt like it's really important challenge and we should address. And then in there, in the room, I see all these, equipment that sensors and plugging into the patients. And then there we will be able to observing all these vital signs, and also that will be time series data. And each patient will then have obviously their own time series observations. Hopefully, by devising smart AI solutions, we'll be able to effectively monitor the patient's condition. Another application is regarding the mobile health, where now sensors have been putting device into different parts of the humans. When I was working project with Samsung, they at that time they were working on the so-called Samsung patch, where they can actually put the sensors as a patch on top of a person's chest, so that we don't have to take it on and off, and we can also wear during the shower. But basically, in there, we will also be able to get a lot of time series observations about the patient, about the user, how their activity, daily activities, and also some of the important vital signs, and we'll be able to hopefully actively monitor the health and fitness of the patients. Another example is the so-called AI for transportation. That is also a huge area where we are exploring in terms of how AI technologies will be able to reinventing how human actually commute. In there, that for example, that we get all these different type of sensors either this is the loop detector on the road, or this will be the cell phone that we're using by everybody, and then we'll be able to actually get the traffic monitoring and then forecasting, so that we'll see what will be the patterns on the road. And especially for ride sharing, basically they want to detect, how many users will be interested in taking ride at some specific time, based on, the user activities, about their spatial and temporal information. We'll be able to supply the demands for the rides in the rush hours or non-rush hours, and etc. So hopefully by now that I was able to motivate you enough that there is actually a large amount of different applications with so many important problems we can address for time series data. And then people by now are fully motivated about all these applications, but what actually happened is that these applications will expand and explode in the past few years. In addition to everything we talked about, we also now see in the brain science and etc. And recently, DeepMind has this paper in Nature talking about how we will be able to use the deep generative models to accurately predicting near-term weather forecasting. This is a really, golden time for research in this area. On the other side, that I would also argue that real-world time series data is actually totally different from what we see as researchers. As Chinese, we always joke about, how people try to browse the website and think, hey, this is a really nice, clean look outfit. And then when you actually get the product from the website, and this is in the real world, when you try it on, it's obviously totally different. And this is really how we do this, in time series research, in all these papers I'm going to talk about, that you will see these are nicely formulated data, that basically that you just see time series observations is equally time space, and then you can plug in different type of your favorite architectures, and then you can produce papers. But what will actually happen is that the real-world time series, they have a lot of problems. So in here, for example, this is an example in the healthcare application where we get a vital signs for the heart rate, and etc. So as you can see, first of all, a lot of them are like missing. A lot of the data, actually, we don't know why it is missing. Most often than not, for this particular case, it could be the doctors just unplug or the nurses just unplug it because the alarm keep on sounding, and they have been so used to it, they're like, oh, just taking all this off. And then they also have a lot of noise in the data, a lot of irregularity. And then we also have not only the time series data we should consider, but also a lot of either structured data or unstructured data, talking about general descriptors, or then we get maybe additional information about the tests and etc. So basically that we are confronted with a series of challenges when we are actually addressing the real world time series data. And that is basically that what I'm trying to argue, that for research in this particular area, that is for when we talk about building some really important foundation models for time series of spatial temporal data, we are actually confronted with these real world challenges that are also very unique to time series data. When we think about protein sequences, when we think about the language's input text, then you never experience things like, oh, there's actually missing value, or there's actually, or seldom, right? I mean, or that there's actually the multi-resolution. That means that the time series, some of them are gathered per minute, some of them are gathered per second, some are per day, and now we need to aggregate everything together, and that is why the multi-resolution is also an important problem. Multi-model, to a certain extent, exists, both text and images, but now that we also have a new beast in the world that is obviously in the room, that is obviously the time series observation, how we can aggregate all the information together from these language and the images. These are more representing the concept and also the semantics, now connecting with the continuous observations, that is more signals. how we will be able to actually connecting all these multimodal data together is obviously a very big challenge. And then some of the data, many of them actually distributed, and also that their applications touches the privacy aspect, and therefore that we need to do privacy preserving machine learning research. So once we have the roadmap, next I'm going to talk a little bit about our research work addressing these different type of challenges. And then I will talk about on the upper part, basically how we will be able to build a foundation model. And then last but not least, I also want to talk a little bit about what will be the frontiers of time series research in the next few years. So next, I'm going to first talk a little bit about the challenges, how we can address them. The first one. Hello? This one. Thank you. Hello? Yeah, now this works. The first challenge is missing data. So missingness in time series is very common. And sometimes the missingness actually coming from various reasons. When we look at them, that they sometimes are actually not missing at random. In all of experiments in the paper, we always say, hey, this is how we generate the missingness, it's missing at this random rate, and then etc. But in real world, that a lot of the cases that they actually not missing at random. And therefore that the missingness actually provide rich information about the patient's health conditions, about the traffic conditions and etc. And that's why we want to utilize them. So given these missingness, then we actually have to have some representations about how we actually represent the missing pattern. This is actually have been done by people before. Basically, one of the things that they introduce is so-called masking. That is, we basically will indicate with 0 or 1 whether a variable will be missing or not. For example, here we have the time series observations where we have the timestamp 0, 1 to 7, and then we have the actual values. And then in terms of masking, it basically says, oh, the value is missing or not. And then another one that we introduced in this paper that I'm going to talk about is that where we look at actually the time interval, that is how long the data actually, the variable has been missing. For example, that we recorded the durations, right? And then for, if this is not missing, we're going to give it to 1, but if this is missing from the first timestamp, we say, oh, this is 1, and then we're going to record how long this has been missing, and this is the second time, the next timestamp is 2, and then now we have a new missingness. We are going to restart, and that's why this is 1, and etc. So this is basically we record how long the missing will happen. And with that, we were able to actually devise this particular solution, which we call as GRUD, published in Nature Scientific Report about a few years ago. This work was conducted by my PhD student, Cui Zheng, and the postdoc Sanjay at that time. Our idea is relatively simple. Basically, we're saying, hey, we try to model the missingness using the masking, but also we're trying to model basically the duration. And in order to model the duration, we introduced this term called decay term, which is basically an exponential of the Ralph rule of a linear combination of the duration, that is the delta t in here. And then for the specific GRU model, I don't need to go to the details, but in the nutshell, basically, if some of us remember, this is the GRU architecture without the blue part, only the black part. We have the input observations, then we're going to, estimate the hidden variables, H, and then we're going to update this longer term hidden variable, another H, one is H tilde and the other H. That is the GRU architecture. And then what we did is that we're actually adding a little bit of the masking and also the decay term. So for example, in here, we basically will add a masking term for the input to decide whether it is actually masking, is actually missing or not. And then for each of the observations, we're going to add a decay term, which will basically be a gauge to determine how much weight the observations will play for estimating my hidden variable. And then basically that we want to decay on the last observation. This will be a mix of everything. One is about what we actually observe. If we don't observe this empty, that is masking will be 0, it won't play a role in there. And then we're going to look at other terms. One is xt prime d. This is basically the previous observation. So if it is there, then we're going to utilizing them with a decay term that we modeled and introducing here. And then if it is also missing in here, then we're going to also have the x mean, that is basically the average of the observations for that whole time series observations for that particular variable. In this way, we'll be able to actually take into consideration both whether the missingness or not, and also the duration term, so that we can better making predictions. So quickly, in terms of the experiment results, we evaluate this on the healthcare data set, MIMIC 3, and also the PhysioNet. At that time, we literally tried about 30 different variations of how we can do this decay term and also how we can do the masking. But in the end, this is what we settled on, and then we were able to beat the prediction performance for mortality in terms of AUC scores with the state-of-art methods at that time. So, so after our white paper was published, we didn't expect, this is going to be a big thing. We were thinking, oh, this is going to be one version of addressing the missing data issue in time series. But what happened is that people always just take for by default to say, oh, there's already a solution that's utilizing them without actually devising new solutions. So this is pretty much still remain more or less the state of art for addressing missing values. But I think that with the new architectures and with the new technologies, I'm really hoping people can addressing this particular missingness challenges. And I think that's basically one of the major things that we should address rather than devising yet another architecture and testing on a very nicely behaved benchmark data set. Next, I'm going to talk a little bit about the challenge of jointly modeling the space and the time. So this is actually, it was motivated by the transportation application mentioned, where we basically want to predict the traffic across different time and across different locations. This work was done by my PhD student at the time, Yaguang Li and Rose Yu. So what they did is that they're trying to jointly modeling the spatial and temporal dependency. It wasn't that obvious at that time. What happened is that we try to look at all the different type of architectures. By then, there's already different type of sequential models we'll be able to use for modeling the predictions for the time series as the next time step. But there has been limited work around modeling the dependencies about different locations. And that is where we came in to say that, hey, we can actually model the spatial dependencies with the so-called diffusion convolutions over the graph. And then once we have that, we will be able to do a sequence-to-sequence modeling learning with the encoder-decoder framework that people are now very familiar with. And then we'll be able to model the temporal dependencies through this augmented recurrent neural network. So next, I'm going to talk a little bit in details. Yes, now it works. The first and also the most important part is really this diffusion convolutional filter, where basically we take into consideration of the spatial dependencies. Here, what we do is that we try to do a combination of the diffusion processes with different steps on the graph. And in order to do that, if everybody is familiar with the graph convolutional neural network, probably you know by now that we can actually represent the data at each particular location using a graph signal. And we call them, as X. And then what will happen is that, let's say that there is this center that is the blue dots in here, this particular location, we'll be able to construct the network or the graph either using the road network, or we'll be able to construct a graph using similarities or adjacencies in terms of the coordinates. And then once we have the graph, the next step is that we're going to have the diffusion process. First, we're going to have this A matrix, that is the adjacency matrix. And then we will have the D that basically will represent the Laplacian corresponding Laplacian matrices. And then we're going to have this zero-step diffusion, that is basically this graph signal is centered around the starting node, and then we're going to diffuse the information to its adjacent node, but with one step, and then with the nodes of the neighboring nodes of the adjacent nodes through the second step, and then we can diffuse them through the k step. And then in the end, we'll be able to say, oh, we actually have this X, that is the diffusion convolutionary filter that we constructed the sum of all these k steps through this equation. That means that we'll be able to actually take into consideration how the neighboring nodes, their traffic condition will affecting my traffic and in the future time step. So that is how we model the spatial dependencies. And in terms of the spatial temporal forecasting, then this will be relatively simple as a sequence-to-sequence learning problem. We do encoder and decoder, and then we'll be able to, based on the history of X1 to X3, we'll be able to predict in X4. And then sometimes that we want to make further prediction, X5, X6, and etc. We won't be able to actually know their most recent observations, because that is also our target predictor. What we do is that we're actually using the so-called scheduled sampling. That is, when we train the model, we're going to flipping a coin to use either the estimated prediction for the previous time step, that is X4 tilde, or we use the ground truth so that we can have a flipping. And then addressing this, improving this multi-step ahead forecasting. So this is, the model called as DCRNN. Later, we test this on different traffic application data sets. At that time, there's only limited available. One is the Los Angeles, and the other is in the Bay Area, where we're able to compare with the state of our results. At that time, we're able to get really good performance in terms of forecasting horizons on both traffic data set. So after the paper was published, then I also did my sabbatical in Didi, that's a Chinese Uber. And then when I got there, I realized they already implemented this within their platform. So one of the things that this algorithm provides is really the robust solutions. That means that comparing with a lot of the solutions right now, because they consider the spatial and temporal dependency, the prediction results is very sparse, very robust. And this has also been adopted by other ride-sharing companies for their internal forecasting prediction. So this is another example where we're addressing the spatial temporal dependency. The last one I want to give example addressing the challenges is about the multi-resolution. So multi-resolution is a very unique challenge for time series data, because the data was sampled at different time stamp, or collected at different time resolution. A natural thing we want to ask is that how we will be able to address them. So challenges in there is obviously very clear. They sample at different rates, and then there's all these multi-scale temporal dependencies, and then there's complex processes underlying the generation mechanism. At that time, when we look at the problem, we were like, hey, let's see that if there's any good solutions. And this is what we found. People use either the single rate models. Basically, they will fine-tune all the observations to a uniform single sampling rate. Obviously, we have to do some pre-processing. Either people use a common filtering of our model, and etc. But basically, that means that that if we data collected as different, let's say second, hour, minute, and etc., we just say, hey, let's do pre-processing. Everything is at the same sample rate, that is basically per minute. And obviously, something we have to sample down, something we have to fill in the missing values, etc. This is what we mean by single rate. And then the other is obviously that we have simple imputation. If we want to do this multi-resolution, why don't we just do this imputation? That means that for each resolution, we're going to fill in the missing values. And then there's also some related work where they started talking about using some multivariate discriminative model using hidden Markov RN, etc., so that they can generate the hidden states. And these hidden states will obviously generate the multi-resolution data. So we think that these may not necessarily be the best solution. And especially at that time, deep generative models started to become a really big theme. And that's why in this SML 2018 work, where we developed this multi-rate hierarchical deep Markov model, we call this MR-HDMM. Basically, we construct architectures so that we'll be able to fill in the values we do not observe at the resolutions they don't collect data using the deep generative model. And then at the same time, we will be able to model the dependencies across different resolution. So I won't have time to cover the details because then that turns into another talk. But if you're interested, definitely you can check out our paper. So by now I talk three major challenges: missing data, spatial temporal modeling, and also the multi-resolution. These are things that are really the unique challenges that all these architectures like transformer or many other neural net architectures were not able to address. So I think these will be challenges that we as researchers in the field should really address. Next, I'm going to talk a little bit about the new era of time series modeling. So, that ever since last year, we started to seeing a large number of different type of papers published on time series forecasting. As we welcome, the citations for our paper, I also started noticing that I cannot keep track about how many models have been published on these different type of forecasting results. So, and then the first thing I ask my students to do is to say, okay, we need to catch up. Let's try to see what exactly happening right now in the world, and let's do a survey work. So in there that we started to see, because the release of many time series data sets, which I'm going to talk a little bit later, either on traffic, on weather, and many other specific applications we work on. And then that means we have benchmark data set, we can bound on them. And then there are many different models have been developed. For example, you may have heard a lot about the transformer-based models. One of them is PatchEST, even though very recent work and started to attract a lot of interest. And then we also have graph convolutional network-based models. There's also the self-supervised learning model. And there's also very recently, a few months ago, people started to talk about linear model can also work really well. So it causes a lot of confusions in the field. That is, what exactly the right model and architecture to work on, and how we will be able to actually address these fundamental challenges. So in the summer, I asked my students to say, hey, let's take a look and then let's run all these models on these benchmark data sets and see if we can get any generalized observations. Here we go. So this is what we did. For time series, there's typically we have short-term forecasting and also long-term prediction. And that is why here we try to differentiate them. And we're also looking at, as I mentioned, there is the traffic data set in Los Angeles and Bay Area. And then the solar energy, that is the energy data set, and this New York taxi weather data set. This is basically, most of the papers using these data sets. They call it benchmark to making predictions and publishing their papers. Already motivated well enough, hopefully by now, that these are still very toy example. But this is basically most people started. And then our observations for this is that for short-term time series forecasting, it seems that transformer-based methods actually work very well, relatively well, in the sense that you were able to get very good prediction performance, the top one for most data set. And and then another one, Informer, which is also a transformer-based approaches. But basically that for short-term prediction, transformer were able to beat it, to get to the task really well. And then for long-term the time series forecasting, that means that we're predicting, many steps ahead, maybe, 10 steps ahead, 15 steps ahead, or even 50 steps ahead. And then in there, we observe is that seems that transformer-based works pretty well, but sometimes the linear methods also are very popular. But I would also say that a lot of these data sets are relatively simple forecasting tasks, and that is why that we cannot come to a conclusion. So we submit this paper to the NeurIPS benchmark data sets, benchmarking and data set track didn't get accepted. I think one of the major complaints we got is also we do not have a conclusive results in terms of which method works really well. So we were puzzled in terms of what we should do, but at the same time, we got to the other point. That is, when we look at the success of the large language model, it seemed to say that, hey, maybe let's not worry too much about the architectures or which method actually performed on these toy data sets. Maybe we should look into something even bigger, looking at even the bigger scale data and utilizing the power of that. And that is really coming to, by the end of the summer, we come to this conclusion is that we need to work on time series foundation models, and that's what everyone was talking about. And by then, there's already some discussions about it. In this paper, this is actually presented in NeurIPS. They call it LM for TS. It is a large language model for time series by Tencent researchers. And in there, that they basically are actually looking at different type of architectures, but more importantly, in terms of how we will be able to pull off all the data together and building this foundation model as what the language model is doing. And then in terms of the representation of the sequential input, in terms of the futures, and people can use patch or they can use 2D conv or position embedding, etc. And then in terms of the backbone, people have tried many different things, either using large language model directly, using transformers, or using linear models. Obviously, there are many challenges we also are confronted with. I'll say that the first one is actually what I'm listing here, separate training for different tasks. So when we look at the time series data, they actually coming from very different domains. It is very difficult for us to think, oh, the time series observation in the traffic, how they will be able to help, stock prediction. That would be great, and then we can make money, right? But it's not very clear. That is transferring across different tasks. Is it actually reasonable? Is it something we should do? Or we should do like task-specific ones? And the second thing is that obviously there's additional text information. We are surrounded with the world with human working on this data set. And in these scientific domains that we work on, there's all these literatures, there's news around the stock, and therefore there are many textual information we can utilize. We cannot just survive by utilizing time series observation only, because these are the signals. We want to compensate them with the semantics. Last but not the least, there's also the distribution shift. That means that obviously that we have to do this fine tuning to the specific tasks we're working on anyway. And therefore, these are all many exciting things are happening, but at the same time, there are many challenges. So what we did as this iClear submitted work in October is that we look at two things. The first thing is that we want to say, hey, how we will be able to build this foundation model with additional text input. So right now, we don't have a very good standard data sets to do this, and that's why we construct this data set. There are many different areas we worked on and trying to identify, but in the end, that we started to work on the financial application. Basically, we think the contextual information from the finance, for example, news, and also the tools potentially could help giving indicators. But obviously, the main challenges is how we align the time series observations with the news that published at what specific time, right? That is really a major challenge. And that's why that we construct this data set where we have the time series collections, and then we get the stock, and then we're also able to get the data from the so-called GDALT data set, GDALT database, where you get news from or financial news around the companies. Thank you. Hello? Yeah, that was working. And then what we did is that we also need to do a little bit of the text processing. Basically, we have to scrape the articles around this particular company, and then having the summary. And then in the end, that we will be able to generate the word embedding using the AI models that we built internally. So after that, this is what we did. That is, we try to have this model where we have the time series input, and then because time series traditionally that they are analyzed through the decomposition of the trend, seasonality, and residual, and that's why we want to do that in the first place in order to remove the different seasonality or trend and etc. And then after that, we will be doing the patching and then concatenate the information from both the time series and also the text encoding. And then we put them into the model. People have used Llama, ChatGLM. We were using the GPT-2 as the large language model architectures. And then we do the decoding, and then in the end, we can do the forecasting. So this is basically the architectures of how we will be able to incorporate the contextual information. On the other side, that we also want to utilize this in a more reasonable, in a more interpretable way, and that is why we also did a little bit about the soft prompting. Instead of doing the random initialization, we collect the corresponding text data in our original prompt, and then we will actually adopt them into these prompts. For example, we say, oh, this company from the financial report, they already have this net income, and then some of the share information, and then plus the time series embedding we learn. And then we hope that we will be able to generate different prompts, for example, the future value with the given trend, and seasonality, and residual, the time series observations, to generate different type of numerical inputs prompt as well. So obviously, this involves a lot of engineering work. We can do endless, like a never-ending prompting design to achieve the goal. But that's what we tried in paper. So in the end, that we're comparing this, with the either the GPT, which already using the contextual information, or these models which uses time series observations only. We can see that our model, we call it as tempo, we're able to achieve a significant improvement, jumping from 0.002 to 0.01, that is the error rate, sorry, decrease the error rates. So this is, what we get as an initial attempt to incorporate the contextual information together with the time series observation. Another thing we do is that to answer the second bullet I mentioned, that is whether it makes sense that we are able to actually doing this cross-domain training, that is collapsing all the data from all the domains and training one unified generalized LM model for time series. So what we did is that we said, okay, now we want to actually have the data sets that from other domains, trying to use that to predict the energy domain or the traffic domain. So we get data from the weather data and also from the other transportation data, and then we try to predict, the energy data sets. So here, what we see is that if we simply or naively doing this without considering too much about all these unique properties of the data sets, then the results are pretty bad. MSD, when you look at them, is really very high, like 0.3 and etc. And then when we try to get, utilizing the recent one is ChatGPT for time series, then the results are getting better. That means that with some consideration of unifying the time series observations and building a foundation model, we're able to get some reasonable good results. But for ours, where we actually consider the seasonality and the trend and also the residual decomposition. With that specific sequence of these three types, we're able to actually get a very good improvement when we try to make some near-term predictions and even longer term that it's some good improvement, but obviously not as obvious. And the similar happens for the traffic application. So this is our exploration by now, is that it seems that there is some hope we will be able to actually learn a generalized model as what the language model is doing. But there's still many, many steps that we hope that we have to address before the claim that, hey, now we have LLM for time series model. But the progress never stops because there are all these startups that people have already developed and get a lot of VC monies around them. I think that there's a lot of interest in both industry and academia in this long line of research. So next, I want to talk a little bit about the frontiers for time series foundation model. But I want to check how much time do I have? Oh, 10 more minutes? Oh, wonderful. So once we build a foundation model, it's not the end of everything. We think that there are also quite a few research directions still we need to consider. This is probably not unique to time series, but is very important for time series. That's why I would like to mention them. The first direction we think is important is about this physics-informed deep neural network or deep learning model. So when we work on these physical models, right, and a lot of the data we collect are from physical world, we actually will get access to many different types of physics knowledge. For example, that we can have the classical mechanics, we have the symmetry in terms of the equivalence or invariance under the symmetry group of the equations, numerical methods, dynamic system, with the Kuhlmann theorems, common filtering, and many miscellaneous analytic domain knowledge. And these additional information have been the foundations for, let's say, physics research, for material science research, and for many others. And they have been incorporated into the simulation model people have built. And therefore, that it is very difficult to say, hey, we totally dump these and then just to go with all these data-driven approaches, because data can be easily fooled, and also the data quality could be bad, and also that it could be sensitive in some areas that we have limited observations and etc. All these inspire us that we need to actually incorporate these domain knowledge together with a data-driven approach. And in terms of this area, this is a big area. We call this as physics-informed machine learning. The central idea, obviously, is trying to integrate both the prior physics knowledge together with the data-driven approaches. And then there's actually two main campaigns in this area. One we call this as machine learning for physics, basically that all these are serving as a tool using AI models to solve some of the simulations. For example, they can have surrogate simulation, they can have data-driven PD solvers, counterfactual analysis of the physics dynamics. There's a lot of research work have been done, basically trying to improve the status quo for existing simulation system. On the other side, we also work a lot on this, is that we try to incorporate this physics knowledge inside the deep neural network model we can incorporate. For example, that we can have all these different type of models that we build and then incorporate the domain knowledge, as I mentioned in these, for example, PD equations and etc., so that we'll be able to get a robust and better prediction model. So in there, that this is one line of work that my PhD student Songyong So did. That is, he was using this graph convolutional neural network to incorporate the physics knowledge, so that we will be able to achieve, the advantage of both. So we tend to classify them as two major threads. One is so-called general inductive bias. That means that we build this model and then we try to incorporate the physics knowledge inside our domain and into the physics, into the deep neural network model. A classical example that we did is that we developed this physics-aware graph convolutional neural network, where we incorporate the PD equations as a function that is basically that a temporal difference is a function of a spatial difference, and then incorporate this particular domain knowledge inside the neural network to get prediction results. Another example where we work on is that we do this task-specific ones. That means that for some domain areas where we have limited amount of data, then we basically can utilizing the data from other areas to build this neural network model. But then when we try to generalize this area with limited amount of data, we want to guide them through the neural network. So that is basically the second line of research. Obviously, there's many things have been developed in the meanwhile. Right now, there's a huge interest and also bursts of energies. So I think maybe last week or a week before, that DeepMind also released their efforts in terms of utilizing the new AI models for material science. And there's also, we're working with the domain experts for AI for drug design. All of them will have to consider, the physics knowledge in order to make the model stable and robust. So that is really one exciting area. And a second one we think that is really important is the causal models. So in terms of causal models, this is causality versus deep neural network. This is a never-ending discussions about it. Obviously, this causal structure is extremely important, and making inference on top of it is also in very much demand. But both of these tasks are actually extremely challenging. For example, that given the causal structure, you want to do the inference, right? And then you can do build different models to do counterfactual recurrent neural network, or counterfactual or causal-based graph neural network, causal transformers, in order to do counterfactual outcome estimation, right? And then another task also very important is that we do not know the causal structure. How we will be able to actually automatically discover them? And this is what we call as the causal discovery. Again, this is extremely difficult task, and even in time series, this is even harder. And so in about 10 years ago or 15 years ago, we started working on this particular area. We call this Granger causal model for time series, where we're basically trying to utilize the Granger causality, which is not actual true causal per se by Pearl's definition, but it's very useful, in the practical applications. And the way that we do this is that we basically try to uncover the temporal dependence among the multivariate time series using simple penalized autoregressive models. And then with that, we'll be able to recover what is the temporal dependencies between different time series. And then we'll be able to utilizing them to review the dependency structures in climate change or in the gene regulatory networks to provide, scientific discovery tools. And the other thing is that we can utilizing them to actually build a better prediction model. So we've addressing many different challenges in practical application. So if you're interested, definitely you can check them out. So we stopped working on this particular area about 7 or 8 years ago, thinking that there might be some better solutions on this. We just recently started reworking on the problem, and to our stand, that is, there's still very limited progresses that it can actually work in this domain. And people are still relying on simple linear model for the causal discovery. There is a lot of recent work talking about using the deep neural networks to actually help the discovery. I think the major challenge in there is that we're still bounded by the limited amount of data. And that's why that, linear models still perform relatively well and robust. We try this different neural network discovery processes for one application we worked on, but the results still are not as good as our simple method. So, but I think that this is a really important area. Hopefully with the growth of the data, we'll be able to get a breakthrough in this area. So I won't have time to talk about this, but we also have work on counterfactual estimation, counterfactual outcome estimation given the inference structures. So last but not the least, I also want to jump a little bit on interpretations. Interpretation is also highly relevant and related to causal. So these are kind of sometimes hand in hand. I wouldn't say that this is actually totally separate areas, but they have their own particular community, and that's why that I want to, point into this direction as well. So for interpretable machine learning, that is also a very important but also challenging problem. So when we first look at what is model interpretability, based on this definition, it says it is the degree to an observer to understand the causes of a prediction. Then here, there's three factors we need to consider: observations and what do we mean by understand, and what do we mean by causes of prediction. All these are not well defined, right? And depending who are the observers, my understanding of interpretation could be totally different from other users about neural network models. So usually there are two different types of observers we see. One is end user. These are the people I work with, the domain experts. But even for them, doctors would understand rules, right? But for the climate scientists, they're very good in math and physics, and therefore they can understand mathematical equations. And then for machine learning practitioner, we want to debug the model and how these information interpretation help us improving the model prediction results. I think that's really the important thing. And then therefore, this is more like the blind touching the elephants. Many methods have been developed, but there's no conclusive sense in terms of what are the right tools to use. And then in terms of the examples of the model interpretation, people have looked at many different ways. You probably have seen this a lot. For example, you were given an image, we see, oh, these are the important features they identified. Or we can do the model representation to see the clusters and to see, hey, the representation they learned are meaningful. Or we use these decision tree or decision rules so that human can understand this to a certain extent. And the research work can go on, and I just want to summarize them to say, hey, they can have direct interpretation or indirect ones, or they have global interpretation, that is understanding the interpretation of the whole model, or that they can do local interpretation. That means that in this particular neighborhood for that specific testing data, how we will be able to actually interpret the predictions. Obviously, the line model is one of the most famous one, and we really like it a lot because it's one of the simpler approaches, very robust and providing information needed for most of the interpretation tasks. So, and then what we did is that we were thinking what the interpretability can bring us, because we use these different type of interpretation methods, showing them to the doctors, showing them to the domain, to climate scientists, transportation experts. They're looking at our interpretations. They were like, oh, I see something that I know. Oh, wonderful, you're doing something meaningful. And then they see something they don't know. They're looking at it, will be like, interesting. And then they walk away from the meetings without any particular action item. And then we were thinking, oh, this is probably happened because of the following reasons, right? The first one is interpretability versus information loss. That is because whatever we're interpreting, it's not exactly what the neural network is doing. Because these rules that you can obviously learn a decision tree 20 years ago, we can show to the doctor, you can get similar results, right? Then that means that whatever that we're interpreting, there's a huge information loss or reduction of the information of the neural network. So we do not want to do this because it's not really the essence of neural network. The other thing is that interpretability for downstreaming applications. That is, okay, once we have the interpretability, are we going to use this to actually debugging the model? Are we going to use interpretability to actually building a better model that is more interpretable? I think these are kind of not answered question yet. And last but not the least, obviously, that with the interpretability, how this is connected with all these issues we're talking about: AI ethics, fairness, robustness, and etc. These are all hot topics right now. And it is still, there's some, a lot of reasonable good work among it, but obviously there's a lot of research still need to be done. Here that I just want to give you one possible direction we work on and to give you some food for thoughts. One of the things we started to look into is the so-called feature interaction. we think that the neural network is a general function approximator. That means that they basically just approximate the ground truth functions, and then in the end, they will be able to use this sophisticated optimizations, solving this optimization using the stochastic gradient descent. And therefore, that what it essentially captures is this higher order interactions between the features. So why don't we actually discover that, right? First, I want to just mention what is feature interaction. The feature interaction means that basically that we have the main effect, that is the linear function. If this is the ground truth function, then this is the linear combination of the input feature. We call it the main effect. This can be captured by most of the machine learning model we worked with. And then the other thing is so-called interaction effect. This is something we're interested in discovering. And that means that, these features interacting with each other pairwise way, or let's say jointly X1, X1, X3. Why do we want to care about modeling feature interaction? Because if we can model the feature interaction really nicely, then it will improve the model accuracy. That's where, the power of the neural network comes from. It can help the prediction, and especially capturing the ones that humans are not very good at, because we're very good at capturing the main effect. We observe, our brain analyze the main effect. But when they have higher order interaction, that's where we have to resort to tools. And then hopefully this can also help us build a more interpretable model that can achieve similar prediction performance as the neural network. And then the history of feature interaction has been there for a long time. It's not something new. The statisticians, when they first study statistical analysis, that's what they do. That can be dated back into several hundred years ago. But what we did in this work by my PhD student Michael Zhang at the time is that he developed this method called neural interaction detector. Basically, that we were able to actually discover all the higher order interactions captured by the neural network by looking at the weights of the neural network. And then after that, we will be able to actually provide the interpretations of what higher order interaction the neural network actually captured for this particular data set. And then finally, we're able to build a generalized additive model by only using the terms that we captured. And then the prediction performance is as similar as the neural network model for tabular data. And that's really, making us more motivated to pursue this direction. I won't have time, to go through the details, but if you're interested, you can check out the papers we have. But basically that we first, using the first neural interaction detector work, we're able to interpret everything for multi-layer perceptron. But looking at the first layer of the hidden nodes, and then later we try to solve this problem of higher layers of hidden nodes by disentanglement. And then we started expanding the multi-layer perceptron to all these other models via MAHI, where basically we can interpret any type of neural network structure architectures. And then last but not least, it's not last, this is his last work before PhD, is that he developed this archipelago. Basically, we are able to identify both the feature interaction and also can attribute how much they actually contribute to the final predictions. And then last year, NeurIPS, that my new PhD student James were able to publish this work where we build this generalized additive model, which achieves similar prediction performance as the more complex neural network model on tabular data. And now he's working on image data, and we also just recently submitted a paper to iClear on interpreting the large language model. So with that, I just want to summarize what we have gone through. I know I talk a lot of things. What I want to summarize is that I think there is a large amount of open questions in this area. There's all these unique challenges such as multi-resolution, missing data, multi-model, etc. that is unique to time series that we do not have really good solutions. And we think there should be more work devoted on this, addressing these practical problems in time series rather than beating the benchmark data set with the really nicely formulated, well-behaved data. And then, in terms of research area, foundation model is important, physics informed, causal model, another area of federated learning I didn't have the chance to talk about is also very important for distributed data and also interpretable machine learning. So with that, I want to summarize, to end with this particular slide, that is, I feel the most nervous in my whole career in the past few months. I tried to talk to a lot of people because I felt like I'm this person standing in here, and obviously there are many of us, and just one person in here. And then I see the tsunami of these foundation models just right in front of us. I feel very excited and also intimidated at the same time. And hopefully, we will be able to ride with the wave and addressing all these significant challenging problems that I motivated at the beginning for climate change, for health, for smart transportations, so that, we can enable scientific discoveries in general. So with that, I'd like to thank my PhD students and the funding agencies, and also, again, the organizers for inviting me to give the talk. Thank you very much.
Thanks for the talk.
Any questions?
Yeah, I have one with Mike. So you mentioned 5 challenges. And first of all, thanks for the rich topic, a lot of information. So there you have 5 challenges. And you were working on missing values. And I think it was in a healthcare settings. I mean, I think you work with mimic and one physio-net. So I was wondering about the transfer learning. I mean, because these healthcare systems different population, right? What about if you want to transfer this model to other healthcare systems, to real healthcare systems as well? How challenging is that? Because this is missing value, this model is working with this population. With the bias. So how challenging is this?
Yeah, I think that's a really, really good question. And when we work with the doctors, and I think personalized medicine is extremely challenging, but also very, very important task. I think that for the personalization, there have been many different solutions. As you mentioned, we can do transfer learning, right? Or that people also started to look into meta learning. And now, obviously, that a general thing that people now throw out of the pocket is to say, hey, now we build a foundation models, and then you can do fine tuning on a specific patient. So I think these are really very much have similar spirits. That is basically that we want to build a general model by looking at across different patients, right, capturing their specific characteristics, and then we build this model, and then to the specific patients. Then they have their own data. Sometimes can be very limited. We recently working with the doctors to looking at, the ovarian cancer by looking at the medical images, the protein sequence data, mostly genomics data, healthcare records, and etc. In there, that the data is very limited. Sometimes, as you mentioned, it's missing. For example, I only have the patient's records for this particular patient, or I only have the medical image data. I only have the doctor's notes and also the patient's genomics data. So that means that the data in the healthcare domain is not only missing, but also fragmented so much. It's a very, very challenging problem. So several years ago, we started working on this. We call this as a fragmented data. I write a whole proposal about that. Didn't get funded, but I think that there's still some hope we will be able to address them, but given right now the data are much more fragmented, then the technology may not necessarily being able to provide a good solution yet, because most of the problem right now is that really getting this large amount of data in healthcare to build a good general model. and then to specific patients, then either for missing data aspect, there's some, I can give an example, not specifically in healthcare, but this is what we did, is that we've developed this generative model to fill in the missing values for specific for specific individuals. This was the paper we published in AI Ethics. That is the first AI Ethics conference where we get the criminal records, where they have, the records and also the police notes. And then we try to make predictions on whether the patient, this particular person should be bailed or not. In there, again, we have similar challenge where that we have probably the missing value, the value, for example, the police report is missing. So at that time, that's about 5 years ago, what we did is that, hey, now we have deep generative model, we can fill in the notes, we can fill in the police notes and then making predictions. And then we were pretty happy with the results. We get improvement, but when we presented work, we were challenged very, very hard by a reporter from Science magazine. It says that you cannot fill in the missing value if the police report is missing. So that means that it's not only the technology, but there's also a lot of ethics issues. That is, for example, we say, hey, we built these models by filling the missing value with the generative models for a patient to predict, what type of drug to use for this patient. But there's probably a lot of ethics considerations whether we should actually fill in and generating the missing genomics data. So I think from that perspective, I think the technology is there. And first of all, they may not necessarily perform really well yet because of the limited amount of data. The second is that ethic-wise, is that actually we should do using the technology to fill in some sensitive information. I think from both perspectives, then we don't have a good solution to give you a short answer. There's some, hacks that doesn't mention filling the missing value with the generative models. But I think that we should pursue other solutions. So it is, that's why I said this is a really, really good question. I don't have a very good answer. The technology, for example, deep generative model, meta learning, or even fine tuning is there. But I think that we have to work with the domain experts to devise the ethically good answers for that. Yeah.
Thank you.
Yeah. Any more questions?
Yes. Develop models for an anomaly detection based on that models on models.
Yes, so I didn't have time to mention this, but we do some work around anomaly detection for time series data. In there, that for anomaly detection, we also started to look into cases where basically you can use a deep generative model, obviously, to generate probabilities, and then whenever the probability, the statistical test says, oh, does not conform with the typical observations generated from this model, then this can raise this anomaly. And then there's also these supervised learning approaches where you have the labels of anomaly, then we will be able to detect them. So that's another line of work for supervised anomaly detection. And then several years ago, we also looking into this causal structure-based anomaly detection. Basically, we think that especially for many of the physical system or even for a patient, then whenever there's anomaly, typically, this is something changes in terms of how different components affecting each other. And then if we learn the causal structure, which is relatively stable and much more robust to the noise, then we will be able to actually detect anomaly better. So basically, in anomaly detection, we are confronted with a few challenges. The first one, as I mentioned, is robustness. That is, that the reason why the nurses pull off all these sensors is really because that the anomaly, the false alarm rate is too high. So that means that we have to really have a robust anomaly detection algorithm. In order to achieve that, as I mentioned, the causal structure might be something we can consider. Deep generative model is another one. And then the second one is about interpretation. That is, a lot of the time when we look at the anomalies, they just give us score to say, hey, you have anomaly, B, 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 right? And then the nurses come to here, oh, nothing wrong. Let's just ignore them. Then why we alarm anomaly? I think that's also something that we should look into and explore. But in that direction, basically that we will look at the causal structure, but many other researchers also trying to build the generative model or neural network structures, and then they interpret, that is the interpretable methods I mentioned. And then with that, they will be able to provide interpretations for anomaly. So, and then the third challenge we're facing right now as we speak is this multi-model. That is, it's no longer just time series observations, a lot of them involving image data and also text data. Then how we actually build this multi-model anomaly detection, especially for healthcare application. Another application we work with the doctors is actually the neurosurgery, the robot surgery, basically that we will be able to see the videos of inside abdomen when the doctor operates, and we also will be able to get the kinematic data. That's a time series observations. And then we try to say, hey, if we can actually send alarm signals when we see something is wrong. So that means that in all these natural applications, this will be multimodal, and therefore how we build this foundation model for multimodal and then doing effective anomaly detection. That's also a lot of work. So yeah, I guess to answer directly back to your question, yes, there have been many different methods developed for time series anomaly detection, but in terms of addressing robustness and interpretability, and I think there's still a lot of room for improvement.
You can ask. Yeah.
Okay. Thanks for the video for the talk. I have a question for the feature attribution method. Because for you, only use the like line method you mentioned?
Yeah.
Or training group precision here with your model output. So first question is like, does that how many words? This is where my question is coming from. Do you work in a research institute with medical center data and also with maintenance center data? And in there we have to do that, especially for these recurrent, like for example, vibration technology, these local methods, they do very weird stuff potentially, because what you actually do is if you plot your feature acquisition method, you treat the time series as a picture. And for the time series as latent spaces. So in there we have the issue that these methods to be depending on the type of figure you have the base fail. So how do you deal with that, or you face that issue and your these feature interaction method that you talked about? Does that deal with it? Because the feature is not the concept, but the feature is from latent information.
Yeah, I think thanks for asking that question, because I didn't have time to go over them. So that's the reason why we want to look at the feature interactions, because we like Lyme, and a lot of industry practitioners really like Lyme, because there you can get the solution really quick and you get something out of the interpretations. So one of the things that Lyme mostly work on is this IED data. And then this also obviously started to look into the language data, but we just don't think it's general enough. And then what our work for this MAHI model, where I mentioned that we move from multilayer perceptron to any type of neural network architecture is where we try to address this problem. For example, we work on this recurrent neural network, and then we're able to actually interpret the recurrent neural network to say, hey, these are the interactions between these time series observations in the previous timestamp or in multiple timestamps ahead before that they actually interact making predictions. So it's basically a combination of both LIME and also our neural interaction detector. So that's the MAHI model. So if you're interested, I can point you to the paper. In there, we have interpretations for RNNs, and obviously we also have CNNs and graph convolution.
And but the feature is always a time step, basically. It's not a frequency, for example. Any other latent information is time series might have.
Yeah, so for our interpretation and the feature interaction, they're only talking about input space. So we don't have there's no latent space interpretation. Yeah, but I know there's a lot of work, for example, that Bing Kim from DeepMind, she has been working a lot on these concept extractions. That is how you map the concept with the latent structures that you learn. But for time series, it's a little bit hard because, as I mentioned, for language and also the image, they have the semantics, they do have the concepts. It's easier for researchers to say, hey, I'm interpreting through the concept understanding. But for the time series set, it's signals. So that is why it's also very important that we can do the MATI model where we will be able to actually align the time series signals, the semantics with the concept that we know as language and image. I think that's definitely the next step that we can work on. Yeah. Thank you.
We are running out of time.
Yeah.
Thank you very much.
Yeah, thank you, everyone.
Very much.
So you may.
Yeah.
So you.
Estamos por el tiempo. Vamos a continuar con la próxima. So let's continue with the next.
¿Enseguida o descansamos?
Sí, una presentación. Y de ahí. So let's continue with the next presentation. ¿Quién es Eduardo?
Oh,
You,
thank
right?
you.
Okay.
Thank you so much. Can you share the presentation? Okay. Please. Thank you so much.
Yeah, I shared, but it's not displaying, so I was asking. Okay.
Yeah, dímelo.
Hello. Hello. Good morning, everyone. So my name is Prakash Charasia. I am a PhD student, third year at Georgia State University. And today I'm presenting a paper that I've been working on using a federated learning. So on the schedule, you might see the title is different because we changed the title on recommendation of reviewers. So the new title we have provided is efficient classification of SARS-CoV-2 spike sequences using a federated learning.
The fifth one, yes.
This is our team on the left top corner. That's me, Prakash. Then we have Tasleem, Zara, Sarwan Ali, and our advisor, Maria Patterson. He is also here. So let's continue with. Oh, it went to the end only. Okay. Yeah, let's continue with the talk, and we will be discussing all these points. We'll check the methodology, architecture, workflow, data set, and we'll discuss about the baseline models that we have used and the results that what we are doing exactly. So to start with, The introduction, the motivation behind this project is to provide the privacy concerns using the genomic data. So we used a prototype kind of uh, project to implement and as a proof of concept. We are using genomic data from SARS-CoV-2. And it's really highly motivated since, especially after COVID-19, we have seen a lot of genomic data has grown a lot, and we need some privacy concerns to be addressed. So we use the federated learning approach to solve the issue. To process the genomic data and do the classification and other machine learning underlying tasks, we have been using for a long time the phylogenetic trees. That was the oldest method. Then we came with machine learning solution later. They evolved as the better solutions. But all of those solutions has a scalability issue, and I mean, it's very difficult to handle the large set of data which is getting produced these days. So we thought of giving a thought on how we can handle it and how we can distribute it while keeping the privacy. So instead of doing a distributed computing, federated learning, which has been popular since 2016 after Google introduced it, fits completely to solve this problem. So what we did is we used the spike sequence data. Spike is the region which is very essential in the virus to be studied for any mutations for genomic data. So we are using the spike sequence region for the whole genomic sequence. And what we are doing is we are doing the classification. We can do clustering also later on, but we are doing classification right now. That's too fast. I'm sorry. So these are the challenges that we have. The first one is privacy and data security concern. To talk more about it, in COVID-19, we have seen a lot of countries were not sharing data, and they were hesitant, and there was a question like if they are sharing whatever number of cases are coming, whether it is authentic or no. So these kind of privacy concerns can be handled with using the concept of federated learning. The second thing is, as I mentioned, there was underreporting. Because of these concerns, countries were not reporting, and the authenticity of reported data was really difficult. So we have to come up with a solution, and that's why we came up with this solution as a prototype to see whether federated learning would be able to resolve these issues or not. So to give a brief overview what the federated learning is, if you don't know already, we have local models, we have different computation capacities. At different institutions, for example, you can imagine as multiple hospitals or multiple countries, and each country or each local unit has their model and their database that they train on. So likewise, we have 3 different organizations. They are having their own local model and local data that they train the model on. And when we have something which is very local to that organization, we can extract the juice out of it. We can extract the important information which are concerned to the underlying task of classifying the variants for us. So we can move these model weights and local updates to a federated server where you aggregate all the learnings from different organizations, right? So all these organizations, whatever learning they have got out of their local data is basically pushed to the federated server instead of sending the data. To give another brief overview, like if organization 1 has reported many cases of a particular variant, we are not asking that which variant it is evolving. The local model is going to train, it will learn that how the genomic sequence is changing for that variant, and we get the learning in that form of a model weights only. So that way we are keeping data private, and the organization 1 does not have to share the exact numbers, but still contributing in research for the global good. So this is the architecture. As I've mentioned, we have exactly implemented the same prototype. We have 3 models. We divided our data into 3 equal data sets, which we are using for these individual models. We have a federated server, which aggregates the model weight. And then we have a global model, which is sitting on the federated server, which is going to consume all these weights from these local models. And then we have some public data also. We kept some data to train the global model. Maybe some organizations want to publicize some of the data. If we have some random data coming all together, we can use it as the data to train on a global model. So for the global model, we have a neural network deep learning model that we have 27 neurons in the input layer. It is basically coming from the 3 local models for each of the 9 class labels. So in our data set, we have used 9 different variants of SARS-CoV-2, which we are trying to classify. We are trying to classify the it's a multi-class classification problem. So this is the architecture for the global model, and let's talk about the workflow. The workflow composes of 2 main components. The first thing is the genomic data. We have a genomic data, which is basically the sequence. So we need some numerical representation to feed it to the machine learning. So we are using one-hot encoding to encode the genomic sequence and convert it into the numerical embedding. And once we have the feature vectors in form of a one-hot encoding, this is the workflow that we are following. We are splitting the data into global testing data and the training data. And the training data is further divided into 3 models. In real world scenario, we will have automatically all these local data fitted into it. We are just doing it as a prototype. So we are dividing data deliberately, which is not the step of this project if it is implemented directly. So we'll have local model and local data available right away. So all we need to do is do the one-hot encoding, and we'll have the local data. So after this, we train the model with the respective local data, and then all these weights are aggregated at this step, and we get the ensemble model, which is having the learning from all 3 local models. So this is the same algorithm that I have talked about, the workflow. We have denoted it in a pseudocode that how we are doing it. We are doing one-hot encoding, splitting data, splitting training data. The model 1 gets trained on training data 1, and then we have the weights. Model 2 gets training data 2, get trained in on this one, and then we get the weights. Likewise, we aggregate the model 3 weights from 3 different local models, and then we run on a global model. So this is the data set that we've used. We had 9 different lineage classification that we are doing. We divided all of them into 1000 each for each local model. And these are the spike sequence data, which we fetched from the GSAID. So what we have done is we implemented it for the federated learning, and then we have compared it with the baseline models. These are the following baseline models that we are using. So we have spike to vec, WDGRL, which is a deep learning based established benchmark baseline model. Then we have PWM2vec, Spring kernel, Protein BERT is the LLM model that we have, the BERT model. And so to discuss all these properties that these baseline models have to compare, we have mentioned like what all approaches these models follow. So the spike to vec is the alignment free, whereas WDGRL needs aligned sequences. PWM2vec also need aligned sequences. string kernel and protein BERT and federated learning can work without alignment. So alignment is a big challenge in a genomic sequence. We have to have an alignment, which is a lot of overhead. So for the large data sets, it's very popular among the researchers these days to find the alignment-free methods. So we picked few of them which are alignment free as well, and which few of them which require the alignment, but they are like established benchmark which has been used for quite a while now. So privacy has not been preserved in any of these, clearly because all of these are centralized model. All of them needs the data to be aggregated together and sent to the central server where these models will be implemented. So the data privacy is not retained in any of those except the federated learning ones. The communication cost is also very high because when we are doing the centralized approach, you are trying to gather all the data at a central server, which will take a lot of efforts. So federated learning, since you have a split it's kind of a distributed computing. You have a different settings for different organizations where you are distributing the load. Space efficiency, again, because we are using a distributed model set, so we have more space or we require less space to work on. Spike to WAC, WDGR and PWM to WAC are also space efficient because of the nature of alignment free. So because they are alignment free and they generate the feature vectors which are very space efficient. For the runtime, PWM to WAC is the main baseline that we are comparing, but for some reasons, the federated learning, the global model takes a while. So since it is a deep learning neural network and deep learning always takes very big amount of time to process, we don't have efficient runtime when you see it in a larger perspective, but when you are looking at a distributed side, then we are doing some runtime efficiency also by distributing the load. So we plotted some TSNE results to compare these baseline embeddings. I think I should come back on this one later after results, but you can see clearly the string kernel does not have any groups, which was the worst performing method in our results. PWM to WAC was good, Spike to WAC was also good, and you can see the clear groups for the variants or lineages that we are trying to predict. So this is the result that we have got. So we can see that although there is not a significant improvement in federated learning as compared to other baselines, like you can see Spike to WAC is also reaching around 93%, and we are going just a little bit above 93.2 or something on federated learning. But the biggest plus point is like we are preserving the data privacy in here. We are retaining the data privacy, so without compromising on accuracy. So, and when you compare with the string kernel, as I've mentioned earlier, they are not performing really good. And WDGRL also is almost below 90. So protein BERT is also 90% accuracy. So we are having 3% accuracy improved among major of the baselines. Okay. So we plotted the confusion matrix to validate it as well. And we can see that only two variants are making, the classifiers are not able to distinguish between two variants. And the reason was these two, both variants are variants of epsilon, and there is a very little mutation differences in among them. To be precise, on spike region, that what we are using the spike sequences, there is no genomic differences between these two variants. That's why we are getting bad confusion matrix for these two variants. Moving on to the results, we evaluated the results of a local model, all three local models, that how the training and accuracy is improving. So we can see after 20 epochs, we attained pretty much around 94, 93% accuracy with this plot, you can see. So to conclude, we are proposing a federated learning based model for a genomic sequencing sequences of SARS-CoV-2 variants classification. And we are using only spike sequencing sequences. So we are reducing our overhead because spike is the only region where the mutations were happening. And we have seen and shown the result as well that the federated learning is outperforming the baselines while keeping the data privacy. So in future, we like to test with more data and more different type of data, along with making a combination with different types of, like what we have done, this one is like we used all 3 identical models at the local level. So I want to do the heterogeneity test, like if the hyperparameters needs to be tuned at each local model, then how it's going to perform in the global level. So that's what we are looking forward to work in future. That's it. Any questions?
We have time for one question only. If there is one, okay.
Thanks for the talk. I have a few questions about the everything procedure and you are uploading to the server model or trading.
Oh, so here what we are doing is we are running a simple classifier. I mean, above this, if you can imagine, the simple classifier is sending the weights for like the accuracy of that each class, that how much likelihood of that genomic sequence belong to that class is coming out of those as a 9 labels. So above this, there are 9 outputs coming from each local model, right? Out of those 9 variants, which one is which? And we are averaging it out basically. So we are using. So it's the probability of that which class it belongs to. And that is used to initialize the global model. Yeah. Yeah, it's a Fed average. Yeah. So we have done like this is an ongoing project that we are working on. So we have done the Fed max and Fed min also to compare it and to test the robustness. As I've mentioned, we need to check like if we, for example, if a local model 1 has 6 classes, local model 2 has 12 classes, that could be possible, right? Each organization does not have the same equal number of classes. So we are currently working on it, but we are trying to incorporate that one too.
Thank you. And so now we have just 10 minutes of coffee break, so we can go for some coffee and some sugar as well. And we come back in 10 minutes. Thank you very much for the presentation. It was very interesting. And what about, I had more questions, but what about interpretability as well? I mean, when it's important that, because you are working in several scenarios, I saw medical, in health. ¿A la hora que viene? ¿A la hora que regresan? ¿O quieres ahorita nomás la foto? Alguien que no está, Eduardo, no está Eduardo, no está. Since you, the keynote speakers, are the stars, they are requesting for pictures. Okay, yeah. Tú con ella. Yes, please. With them. Yeah, excellent. 1, 2, 3, 1, 2, 3, 1, 2, 3. Perfect. O con ella también toma. Keynote speaker, de después. Un favor, como ustedes son las stars, quiere tomarse foto con ustedes. Yeah, with both of you. Yes, please. The keynote speakers are the stars. Okay. 1, 2, 1, 2, 3, 1, 2, 3. Perfect. Wait, I mean, I want to be there as well. Perfect. Thank you. When is important interpretability? Let's go for the coffee and then, yeah. Yeah, in what scenarios? Because you were doing weather forecasting. There, do you need interpretability? It's not, it's important as well.
They don't want.
How you do the trade-off of performance and